Now that we've done the theory of differential abundance testing in the previous session, let's get some hands-on experience in how to use metagenome-seq to detect features of interest that are differentially abundant between two classes. So in this experiment, we've got 3 dogs, so maybe we're interested in comparing the microbiome composition of 2 of those dogs. So the first thing that we're going to want to do is again to merge our raw reads at the lowest available taxonomy. So the reason we're using raw reads instead of the standardized counts that we used upstream is because metagenome-seq has its own normalization method where it includes scaling factors in the downstream model, and so you have to feed raw counts to metagenome-seq. So we're just going to apply that taxcolumn function again to our phyloseq object, and then we have 122 merged taxa. Again, we're going to filter out really low abundance ASVs that we're not interested in, and we use the filter taxa function for that, and that leaves us with 104 ASVs to work with. So because we only want to work with 2 dogs here that we're going to compare, we are going to compare dogs G and B, so we're going to exclude dog K. So first we just get the indices of the samples for dogs G and B. So we take our sample names for that phyloseq object, and then we, for that sample data of the object, say please only give me the samples that belong to dogs G and K, so that are not equal to K, sorry, dogs G and B. And that gives us those sample IDs that we want to look at. And then again, we use the prune samples function. Feed that subindex as the first argument and the phyloseq object as the second argument. And that'll give us a phyloseq object with 10 samples, so 5 samples per class. And this will probably give you guys 104 ASVs depending on the exact input data that you started with. So let's check to see if there are ASVs in our subset of samples that now only have 0 counts because we have excluded dog K, so ASVs that may have been only present in dog K, we'd want to exclude before our downstream analysis. So we look at the length of the row sums of OTU table phi.temp that are equal to 0. So there are no counts across any of the samples for this particular OTU, and we found that there's actually only one ASV that meets these criteria. So we would like to only keep the ones that have counts, so we're going to remove these empty rows. In this case it's only 1 row, and here we use the prune taxa function. So here we use the prune samples, now we're going to use the prune taxa function also from phyloseq. So we're going to ask it for names keep, and then second parameter again your phyloseq object, and for me that leaves 103 ASVs. So next, the function that we're going to use for the differential abundance testing. So it was built around metagenome-seq's fit-sig function, and that's our zero inflated Gaussian model. And to build this model, and we're going to use the MR full table function from metagenome-seq to extract the results. So the customized function also filters the results by fold change, percent presence across samples, as well as adjusted p-values. And then the results are also summarized as a heat map. So it gives you a heat map of the ASVs that were significantly different between your 2 groups of interest, and also summarizes the statistics as a CSV table. So there's several parameters that you can specify. So here we call it the super.fitsig function, and you can also find that in our microbiome custom functions script. We're not going to go into detail, I just want to show you guys. So this function evolved from my own work where I found I was really doing the same analyses over and over, writing the same code, where I wanted to do differential abundance testing, followed by filtering of the results and making a heat map and really outputting that result in a user-friendly CSV format. So you can also specify a covariate of interest, and for this function I built here, it's really only appropriate currently for two-class comparisons like we're going to do now. So we're going to convert our phyloseq object to a metagenome-seq object, and that's just really two slightly different data structures that include the same information. And so we're just going to convert the phyloseq object to a metagenome-seq object so that we can use it with this package. And that's just because the packages were written by different authors and they have slightly different structures. After that, you have the normalization step where we compute our scaling factors for the samples, and then we're going to build the model based on the specified variable factor. In this case, it's going to be our dog, so dog G versus dog B. Then we actually build our zero-inflated Gaussian model. We specify our metagenome-seq object, our model, and then we extract the data with the MR full table function from metagenome-seq. Then after that, we're going to add taxonomic data for our significant OTUs. So we have taxonomic annotation, and we're going to filter the results by p-value, by fold change, and by the number of samples that have this OTU. And then after that, it's useful to, so this is also the filtering, and then after that we'd like to generate a heat map to actually visualize our results so we can see if it actually makes sense. So just like we previously did, we're going to use that same heat map function, but this time only plotting ASVs that were significantly different between these two groups. So let's give that a go. So it might be slightly overwhelming, all this information I've just given you, but if we just step by step work through the arguments that we need and look at the output, I think it should make sense. The first thing we need is, of course, our phyloseq object with the raw counts. And then we have our factor of interest that you'll have in your sample data phyloseq. So that'll be a column name in that sample data, in our case dog. You're going to give it a file name to save your results. So a descriptive file name, maybe dog G versus B in our case. And then we're going to specify a p-value threshold. So this is for p-values that have been adjusted for multiple testing correction. We're going to stick with the default, which is 0.05. And then you've got a percentage threshold for filtering by the fraction of positive samples for a given ASV in either group. So for instance, if you specify percentage as 0.3, it'll only keep ASVs where at least one of the two groups that you're comparing have at least 30% of samples where that ASV occurs. And that's really important for metagenome-seq, as we discussed in the presentation, to get rid of spurious results that aren't truly significant. And then we can also add a fold change filter. Default is 1.5. You can set that to whatever you want. A title for our heat map, a subtitle for our heat map, and there we include our filtering settings. So false discovery rate, the coefficient or fold change, and then the percent presence that we require in either or both of those groups. A heat map descriptor, so that's just for your heat map file name. And then again we can choose whether we want to order our heat map columns manually, so do we just want to sort them by group so we can have a good view of how the ASVs differ per group, or do we want to cluster those results? Yeah, so then you can also add some extra columns. So maybe we want to add treatment to the top of the heat map, and that's especially useful if you have covariates and you want to see that your factor of interest that you're looking at is not maybe confounded by another variable in your study. Okay, so here we actually specify the factors. In this case, I've said the title of the heat map should be dog G versus B for merged taxa. You can see in the file name there, I specify my filtering parameters. So we've got a fold change of 1.25. We require at least 20% presence in either group, and a FDR of less than 0.05. And here we're going to add treatment as an annotation column on that heat map. We should also define our output directory, so we can just use our working directory for that. And remember, our working directory is how we specified this project. So for me, it would be my home folder /r downstream. So let's run this function and hopefully it'll work. It'll give us some outputs here. So firstly it says 0 of 10 samples were removed due to missing data. So if you have missing data for your sample data, it'll first remove those samples and then it'll run the model. That's where you see these iterations. It tells us dog will be modeled as a binary categorical predictor variable, and then we have 40 ASVs that were significantly different between dogs B and G that met our threshold criteria that we specified, and in this case it was with a adjusted p-value of at least 0.05 or less, and an absolute fold change of 1.25, and a percentage presence in at least one of our two dogs of 20%. So then it writes the results and the model to file. We'll have a look at that now, and it also prints a heat map of those specific ASVs. You can ignore these warning messages. So it also prints the plot here. So now we can clearly see we've got our two dogs, B and G, and it highlights the ASVs that were significantly different between these two dogs. And you can see clearly from this heat map, let's just try and get a little bit of a bigger version here, that obviously just looking by eye, these ASVs were significantly different. So if we look, for instance, at Prevotella copri, that's one that stands out. That's really much higher in dog G versus dog B. So you'll see it's present in all samples, but it's way more abundant in dog G. So that's an example of the metagenome-seq model. And then in other cases, you might find, for instance, this Bacteroidalis ASV, that it's only present in dog G and absent in dog B, and your Fisher's exact test would have also picked that up. So let's have a look at the CSV output table of the significant results, and I'm going to have a look in CyberDuck. So that would be your dog G versus B CSV sheet with our percentage cutoffs. And we can see each row is a ASV that was significant, and then we've got a number of columns here with data. So if you look on this side, it firstly gives us the percent positive in each of our groups. So we've got group 0 and group 1, and to know which was 0 and which was coded as 1, you can see at the bottom here we've got our model, and in this case dog G was coded as 1. So here we have, for instance, for ASV 597, 80% positive in dog B, and none of the dog G samples were positive for this particular ASV. We'll continue looking at this table in the next video.